get started with our first plenary talk. So our first plenary talk is by Dr. Laurie Leshin. She is the 10th director of the Jet Propulsion Lab. She's the first female woman to serve as JPL director. She has held leadership positions at NASA Goddard Space Flight Center, at NASA headquarters. She was the president of WPI and previously served as dean at RPI Institute School of Science. She has way too many honors and awards for me to go down and list them all, but I did want to point out that the International Astronomical Union named asteroid 4922 Leshin to honor her planetary science contributions. So that is pretty spectacular. Yep. So Dr. Leshin is my boss. I have to say her energy is absolutely infectious since she joined JPL as a director of the lab. And with that, Dr. Leshin, if you want to come up.
Okay, there it is. Hey everyone, good morning. Hi, welcome to Pasadena. How many JPLers do I have in the audience, first of all right. This is for you. It's such an honor and thrill to be able to stand up here and represent your work and to get to tell you all a little bit about some of the many very exciting things happening up the road at JPL. And I also understand that some of you are going to get to come up and have a tour during this week. So well done, you. It's a great time to be on lab. Before I get started on this, though, I just have to revisit for 1 second the introduction. So the thing you have to know if you have an asteroid named after you is that it's not going to hit Earth. Mine is one of those ones way out there in the asteroid belt, so just nothing to worry about. Everybody, it's all going to be okay. With that, I am again just so thrilled and honored to be able to be with you. I want to start by thanking everyone attending this conference for the work that you're doing each and every day. Really, at JPL, we feel like we do our work on behalf of this community, on behalf of people who are looking to help drive new measurements, help make sure that data are being interpreted for new scientific breakthroughs, helping to make sure that our scientific data is being used to its greatest effect to impact lives and benefit humanity. And I know, and just from looking down the list of sessions at this conference, I can tell that you all are in all of the right conversations about data today and in the future. And so I'll spend a little bit of time on our Earth Science portfolio, but I'll tell you a little bit about some other things going on at JPL as well, because I know you're going to be hearing a lot more about lots of the remote sensing work that we do. At JPL, we talk about daring mighty things, which is it's kind of our motto, and I've added the word together to that because everything we do, and that's true in the world of remote sensing certainly, is as a team, right? Everything we do is about teams working together, and we can't push the boundaries of what's possible, say, for example, by flying a helicopter on Mars 52 times, like we've just finished doing, and are continuing to do, without incredible teams. So I'm excited to get to share with you today some of the work of some of the extraordinary teams at JPL. I'll come back to Mars at the end, but just to say that we work on big things. You all know about our sort of large Earth science missions, large rovers on Mars, big things going into the outer solar system. We also do small things. We do small technology demos. We are always thinking about how to drive the forefront of discovery and innovation and ingenuity. The helicopter on Mars is a great example of that. So what you may not know is that much about our history, and so I always like to remind people a bit about where JPL came from. It actually started with a group of mostly guys, I will say, because it was the 30s, working on campus at Caltech trying to perfect basically rocket engines. They were trying to use them with airplanes, but and they kind of kept blowing things up. And so Caltech very smartly said, hey, there's those great mountains with the arroyo up there. Why don't you go on up there and get away from campus before you hurt somebody? So they did that, and back in 1936, the first rocket test that sort of established JPL was done up in the arroyo, up in the hills, right where we're located today. And more importantly, for this organization, we at JPL built and launched America's very first satellite, Explorer-1. Before NASA even existed, it was less than 6 months later that the legislation establishing NASA came about after the launch of Explorer-1. And it was because pretty quickly our folks turned from trying to build rockets and engines to thinking about what goes on top of those rockets. What is the science that we can do? And we made sure that that very first satellite had science experiments on it. The Van Allen radiation belts were discovered. In fact, James Van Allen is in the picture hoisting the model of the rocket there, along with William Pickering, one of my predecessors as director of JPL, and also Werner von Braun, from what is now Marshall Space Flight Center. So it was a collaboration back then, but led by JPL. And this really I call us the OG new space company, right? We really started the space age in the US. By the way, later in the program, I'll tell you about one of our upcoming missions, Mars, to bring samples back from Mars, where we'll launch the first rocket off of the Mars surface. It's slightly bigger than that one, but not as big as most rockets you think of here on Earth. And I keep imagining and wishing to have a picture with the head of Marshall Space Flight Center and the lead scientist of that program, and myself as JPL director. All three of those people right now would be women. So that picture, if we were to pose it today, would look quite different. Yeah, you can clap for that. That works. So here we are today, from a small group testing rockets to a campus bigger than Disneyland and way more fun. We are an organization of 6,500 people. We are Caltech employees. Among NASA installations, we are unique in that we are operated by Caltech for NASA. NASA owns our buildings and land, but the people are Caltech employees. So it gives us a little bit of a different flavor, a little bit of an ability perhaps to look forward and innovate in some different ways than does NASA Civil Service Centers, who we collaborate with and work with incredibly well. And everything we do at JPL is a collaboration. As I said, teams are everything, and that's across NASA, that's with international partners. Everything we do is a collaboration. So we're thrilled to work across NASA's science portfolio in earth science, in planetary science, in astrophysics. And we also, sometimes a little known fact, I call these folks the unsung heroes of space exploration. We operate for NASA the Deep Space Network, those set of antennas in 3 different locations all around the globe that are constantly listening to and talking to all of our deep space missions. So we also operate that. I'm not really going to talk more about that today, but I am going to talk about a bunch of our missions across the portfolio. So I'm going to start in earth science, because that's probably the area that you all care about and know about the most, although I also saw there's some planetary sessions and things here, so that's very exciting. So obviously our colleagues at Goddard do a lot of work in earth science as well, but we at JPL do also. We tend to focus in these areas, and increasingly, like all of you, we are focused not only on next generation technology, which we are, on what are the next big missions, but also what are the applications on the ground? Where are we really going to make a difference for people? And so just want to show you a couple of examples of where that's happening. And there are way more that I could show you. I'm not going to talk about eco-stress, where we're working on heat island effects in cities, or about Maya, where we've actually partnered with childhood asthma docs on the ground for this mission that's looking at aerosols, to try and understand what we see from space and what we're seeing on the ground impacting childhood asthma. There's all kinds of really fascinating things like that going on. But I want to talk about, so I've only been at JPL for about a year, so, and in that time we've launched 2 earth science missions. So one is EMIT, which is a wonderful instrument, multispectral instrument that's up on this International Space Station right now. actually designed to look at the composition of mineral dust, which is very interesting and exciting in its own right. But it turns out we can also detect methane superemitters. So each one of these plumes is a few kilometers in size, one in Carlsbad, New Mexico, the other in the Middle East. And we are able to see now very clearly from space where methane superemission is happening, or methane emission is happening. And as you all know, much better than I do, because I mostly study rocks on Mars, that methane, of course, is a very powerful greenhouse gas, which also has a much shorter residence time in the atmosphere than CO2. So if we can actually see where methane emission is happening and do something about it, it actually is one of our best chances to get ahead of global warming in an effective way. And so we're doing that with EMIT. We're going to follow that up with future missions to do that at even higher spatial resolution, to be able to detect even smaller plumes. And so again, it is our hope to provide information such that we can actually make a dent in where we're headed with global warming. SWAT is the second launch that we've had since I arrived at JPL. This mission launched in December from Vandenberg. SWAT stands for Surface, Water, and Ocean Topography. It is a full collaboration with CNES, the French space agency, between them and NASA, and we worked that mission at JPL. So this is the first light images that were just released a few months ago. You are about to start seeing way, way, way more from SWAT because it's just moving into its science orbit. Full commissioning is essentially completed. They're still working on the final data to be coming out, but I just thought I would share these two examples of the revolution that SWAT is giving us. So this is radar interferometry at a scale that we have not achieved before. On the right, you can see this is now ocean topography, and of course we've had the ability to measure ocean topography for a long time. In the inset there, you can see kind of that's actually integration, I think, across 6 different ocean topography satellites. SWAT in its very first measurements is giving us much higher resolution ocean topography, higher spatial resolution, and we can actually get much closer to the shore and understand what ocean topography is doing there. And so it's really going to be a spectacular revolution in our understanding of ocean topography, which is already something we've been working on for decades, right? That's great. The real new thing here is to be following what's happening with Earth's surface water. So water bodies on land. And today, our folks tell me that we have maybe 1,000 rivers and lakes that are gauged around the world. We will with SWAT, and by the way, this is, on the left is Long Island, and the bright pink things you see sort of about 2/3 of the way up there are lakes. There are some other ones in the photo if you look, or in the image if you look closely. We will, with SWAT, now once every 21 days, measure the height of millions of lakes and rivers around the world to about a few centimeters. So this is going to provide a revolution in tracking and understanding the distribution of fresh water on Earth. And I know there are a lot of people, probably even in this audience, really chomping at the bit to get into those data. So we're very excited to have SWAT moving into its science orbit, and that's going to be a great asset for many, many years to come. I look forward, probably next year, you're going to have tons of sessions about data. I really hope so. So huge congratulations to the SWAT team, by the way, if there's any of you here. That's just a really huge accomplishment. Yeah, you can clap for that. And then just what's next? So what SWAT is doing for water, NISAR is going to do for land surface. So our next bigger science launch is a mission called NISAR, which is, because this is how we roll, an acronym within an acronym. The N stands for NASA, the I stands for ISRO, the Indian Space Research Organization. So it's actually one of the largest, probably the largest technical collaboration between the US and India right now is this mission. I'm sorry, I pointed to this thing, but you can't see. This mission, which is and SAR, of course, synthetic aperture radar. So it's a 2-band SAR that is enormous and incredible, and has recently shipped from JPL, where the radar payload was integrated, to India, and I am pleased to report that in the last couple of weeks, the payload has now been mated with the spacecraft built by ISRO, and it is in its entering its final testing and checkout phase, moving towards launch sometime early next year. So this is very exciting. We'll look at all kinds of land surface changes, whether that's biomass, ice, also, earthquakes, volcanoes, all sorts of land surface innovation. And I know, for example, Paul Rosen is probably here somewhere. There he is. If you have any questions about NISAR, you can definitely talk to him. It is going to be extraordinary. That's a 12-meter reflector, that deployable thing at the top. It's a beast. It's really exciting to see. So we'll launch this out of southern India, again, in less than a year's time. So stay tuned. That, too, will be a real game changer when it comes to understanding land surface change. A couple things about a few other missions, and again, I could tell you more about many different earth science things happening at JPL. In astrophysics, though, I want to share with you a couple of things happening in our other disciplines. So, you all know the James Webb Space Telescope just celebrated 1 year of science data. Incredible mission. We built the mid-infrared instrument for that mission. The next big space telescope is named for Nancy Grace Roman, who was a woman pioneer in NASA astrophysics, and I think it's maybe the first space telescope named for a woman. Very cool. Like the James Webb Telescope, it's being managed by our colleagues out at NASA Goddard, but we are building one of the key instruments. So we're building, here it is, in our clean room right now today. I don't know if it's going to be on your tour, because it's a little bit of a hard clean room to get to, but it's being built, the coronagraph instrument for this mission. So one of the goals of the Nancy Grace Roman Space Telescope is to really push the limits of imaging planets around other stars. You all, of course, most of you work on and care about imaging and sensing our own planet Earth. We don't have many family portraits of other solar systems, right? It's very hard to see the very faint planets next to the very bright stars. We know they're there. We've now detected over 5,000 exoplanets, over 5,000 planets around other stars, and we think most every star out there, when you look at the sky, most every star probably has planets. Most every. But we can't see them. We detect them through sort of indirect means. We detect them through their impact on their parent star. In order to actually see them, you have to very, very effectively block the light of the star, even better than I'm blocking the light of these massive things shining down, like to 1 part in 10 to the 10th. Like really, really well block the light of the star so you can see those really faint planets. And that's what the coronagraph instrument on Nancy Grace Roman is designed to do. Very complex optical system. It's like the size of a baby grand piano, this thing. And I think it's going to blow people's minds when we actually really start to see other planetary systems out there. So stay tuned. Roman Telescope launches in about 4 years or so, probably a little bit more. And this instrument is being finished up at JPL as we speak and will be delivered to Goddard next year. So very exciting time as we start to imagine other solar systems and being able to sense them, not just the stars, but the planets themselves, to be able to be detecting photons directly. Very exciting time. And then the space telescope that will come after Roman will do this even better, and we're starting work on that. It's called Habitable Worlds Observatory. So again, with a really strong focus on understanding what other worlds are out there and what they're like and whether they might be habitable and even inhabited. So understanding life on Earth, understanding the potential for life in the universe, obviously huge questions that we are trying to pull apart each and every day. And I sort of feel like on the space science side, we kind of have our own little space race going, which is where are we going to find life first, on an exoplanet or within our own solar system, which that is another really strong focus. Of course, at JPL, our history is being the first to explore nearly all the planets in our solar system, dating all the way back to 1962 when we first flew by Venus with Mariner 2. So just to wrap up, in planetary science, there's a lot of exciting things. For those of you coming up to the lab, you will get to see this. You will get to see this one. In our big high bay coming together right now is our next outer solar system mission, which is called Europa Clipper. So Europa is a moon of Jupiter. It goes around Jupiter about every 3.5 days, and it is water ice on the outside. So it is an icy water ice shell, but we very strongly think, based on prior flyby missions and even Jupiter orbiters, that beneath that icy shell is a global ocean of liquid water. So Europa is an ocean world like the Earth. And our goal is to understand whether that ocean world might be habitable. And so Europa Clipper, and here it is, I will say, in our high bay, in our clean room. If you're coming to JPL, you will definitely get to see this because there's a great viewing gallery. But even if you're not coming, there is a YouTube constant webcam stream that you can watch our fabulous technical folks literally building this spacecraft right now. And it looks even different than this. This was a little while ago. So you're going to see it covered in blankets and more integrated even than this. But it is now fully stacked up and is entering into its final integration and test sequence for launch in October of 2024. So this mission will go to Jupiter, go into orbit around Jupiter in about 2030, and do multiple very close flybys of Europa with 9 different sensors on board, many great remote sensing instruments, cameras, spectrometers, radar, in situ sensors, mass spectrometers and such, to be and particles and fields measurements, to be able to really understand the environment at Europa. And some of those flybys get down only tens of kilometers above the surface. So we're going to get really close to this fascinating ocean world. And because by the great work of our mission designers who have figured out how to do smart flybys here. And the reason why we do flybys instead of orbit is the radiation environment at Jupiter is just nasty. So if you're to go into orbit around Europa, it would probably only last a couple of months. But with this, multiple up to 40 close flybys of Europa, we could not only get global coverage, but you spend most of your time in the orbit out of the most intensive radiation. And so the mission will last much longer and get much better coverage overall. So we want to know, where's that ice thin out? Might there be places where the ocean might be more easily accessible by future missions? We want to know, are there geysers spitting out like we see on Enceladus, a moon of Saturn, that we might be able to fly through and taste what's in that ocean, right? Understand it. And so our sister ocean world out at Jupiter, which by the way was a surprise, people didn't really expect there to be ocean worlds this far out in the solar system, way back when I was a student, back in the ice ages. It's amazing that we now get to go explore them. And there are ocean worlds around many of the giant planets in the outer solar system. And I really do believe that this is going to be a big part of our exploration for the future. So come by, see Europa Clipper. It's going to launch on a Falcon Heavy a year from October. And that's going to be quite a show as well. And it'll arrive at Europa in about 2030. For those of you, by the way, who might know of the European mission to the Jupiter system, JUICE, which just successfully launched, and congrats to them. They launched before us, but we get there first because, again, we've got the great Falcon Heavy rocket sort of throwing us there. And speaking of Falcon Heavy rockets, we also are going to launch one of those this October, so just 3.5 months from, no, 3 months from now, less than 3 months from now. With carrying a mission to an entirely different kind of world, right? If Europa is an icy or an ocean world, and we also, of course, have visited rocky worlds like Mars and Venus, we have never visited a metal world. And we will do that starting this October with a mission called Psyche, which is going to visit a very metal-rich asteroid, also called Psyche, just to keep it a little confusing. You gotta keep on your toes, right? Main belt asteroid, so it's going far from Earth. And this is kind of true exploration, right? We really don't know what this thing is going to look like. It's going to be fascinating. In this case, we will go into orbit around this metal asteroid. So Psyche, which here is sitting at the Cape, is nearly getting ready to be buttoned up and fueled and get ready for launch. It will launch also on a Falcon Heavy, which if you're a launch geek, and come on, let's admit it, some of us are. You're used to seeing a Falcon 9, which is just sort of the one stick rocket, right? So the Heavy has 2 side cores on it too. So it's kind of like 3 Falcon 9s together almost. So 27 engines. And it's NASA's first Falcon Heavy launch. So there've been a few Falcon Heavy launches, but none of them have had NASA as the main payload. And so this will be NASA's first, and it'll be October 5th is when the launch period opens. So we are headed back to the asteroid belt with Psyche, a very exciting thing, and again, going to allow us to explore objects that are really brand new to us. And then I'm going to wrap up here in the next few minutes by talking a little bit more about Mars and the future of Mars. So Mars is a very exciting place to explore. We are there right now with this beautiful rover called Perseverance. You might hear me call her Percy for short. And with her friend there, Ingenuity, who we sometimes call Ginny, the helicopter, they are together still exploring the inside of a crater which once held a lake. We are exploring a delta in that lake environment, and not just exploring it, but sampling it. We are making small drill cores, each about the size of your pinky, and storing them inside the rover. When we first started doing that, these are incredible rocks. They're really fascinating, and of course, I am a space rock person. And I will tell you, I've worked on these Mars missions in the past, and there are limits to what we can do in situ on Mars. In order to really answer the question about whether life got started in the Mars environment at the same time life was starting on Earth more than 3.5 billion years ago, we really need to bring these rocks back to Earth. And so that is the plan here with the rocks that Perseverance is currently collecting. Here's a little smattering of them. They look like little lightsabers, right? But they're each about this big, about, I don't know, 20 centimeters long, each with a rock core inside. We actually took duplicates of the first few samples we took, and we laid them down in a depot, and then the rovers continued off with the other part of the cache safely in the belly of the rover, and is continuing to add to that, to add to the value of the rock collection that we are taking on Mars. Here's what they look like. After we take each core samples, we take a little picture of the end of the pinky. And if you're a rock geek like me, you can look at some of these and know that some are clearly nice crystalline rocks, like volcanic rocks probably with aqueously altered minerals in them. Some are clearly sediments, especially up here in the upper right. You can see those look quite different than those on the left. And so we clearly are sampling a huge variety of environments on Mars, all of which have evidence of interacting with water. Just a paper published last week about some of these sediments to show clear evidence of organic matter trapped in these rocks. This is what we want to tear apart in great detail on Earth, and these are incredibly valuable samples that we are collecting literally as we speak, as this rover makes its way up onto the delta and then ultimately up onto the surrounding terrain at Mars. So we're going to do this. We're going to bring this back with a mission we call Mars Sample Return. That's Percy there in the lower right, but the rest of this stuff is part of the Mars Sample Return mission, and the easiest thing to do is just to show you a quick video as I wrap up. Let's see. If I click this again, what happens? Oh, you even got the music. Dramatic music is really necessary. So here we are arriving at Mars with our lander, which is essentially a launch pad, right? It's bringing a rocket with it. Percy's already there. Oh no, who's coming to visit me? Yeah, so she probably won't be taking her last sample right then. She'll probably be safely away. But we are going to land quite close to where the rover is. The main idea here is that the rover brings each of these samples to the lander, and the lander has an arm which transfers them into a sample container that's about the size of a volleyball. We're hoping to bring back 30 tubes. They've been loaded into the top of the rocket. There's the rocket. It's about 2.8 meters tall, and we air launch it, because that's how we roll. two-stage solid rocket leaving Mars for the first time, first launch off of another planet. Puts that volleyball into orbit, where it is then captured by a European-built orbiter, massive global collaboration with a NASA-built sort of catcher's mitt on it. That is inserted into a capsule that's about 1 meter across. The whole thing comes back to Earth and spits out the capsule a couple of days out. And for whatever reason, this animation does not show the most important part, which is it landing on Earth. But it does. It lands on Earth in the Utah desert. Actually, the most important part will be me jumping up and down. Like, yay. Yeah, pretty cool, right? Thank you. Yeah, so this obviously very challenging, right? Like build a rocket, fly it to another planet, then throw it up in the air and light it. Woo! You know, we live for this stuff in NASA, we live for this stuff at JPL, but it's all about the science, right? It's all about getting those samples back, and then they will be worked on in by thousands of scientists in laboratories all over this planet. Even a rock core the size of your pinky can be sliced up into thousands of pieces and will be torn apart molecule by molecule and grain by grain, right? So it's just going to be an incredible, incredible thing. And of course, if we can't figure out how to bring back something this big from Mars, I don't quite know how we're ever going to send people. So it's also a really important pathfinder to sending humans to Mars. Once we go back to the moon, Mars is obviously our next destination with astronauts. And figuring out things about the Martian surface materials is also important as we think about how to keep those folks safe. So Mars sample return is kind of the next big thing, along with NISAR, along with other missions in Earth science, along with future astrophysics. We're very excited about all that's to come. And as I close, I will just end with, and some things just keep on going. So how many of you know Voyager 1 and 2? Voyager. People know Voyager? Voyager launched over 46 years ago, flew by the planets in the outer solar system, revolutionized our view of our solar system and our place in it, and they're still going. They are now outside the solar system. They are now on the edge of interstellar space, the first human-made objects ever to be communicating with us from there, and we talk to them every single day. Every day they're sending back information about not only their own health and status, I'm still here, but also what they're measuring and what they're finding. Their particles and fields instruments are still working. And so we are discovering things about the outer edge of our happy bubble here in the galaxy and in the universe that we didn't know, and some of those things are challenging our understanding. This is what we get to do each and every day. We get to explore and understand new things, whether that's about our home planet, about other solar systems, or about other planets in our own solar system, that are going to rewrite the textbooks. And I just think we're incredibly fortunate, all of us, to be able to do this kind of work. At JPL, we absolutely believe we do this kind of work on behalf of a huge science community. So again, thank you for all you do to make sure that the data that we're collecting is making the most impact in the world. Thank you so much.